Yeah, we need to use it. Okay. I think the gain's up a little high.
What's that?
I think the gain's up a little high. I don't know. Is this too loud or? Okay.
I'll test it from back there, but
Is there an AC outlet? Okay.
All right, good afternoon, everybody. Today we have Mark and Kirk Lenigan. Mark obtained a Bachelor of Science in Physics from the University of Michigan Dearborn. He was a major technical contributor to the Champaign-Urbana Wireless Project and the Detroit Wireless Project. He puts his physics, wireless networking, and other talents to use in a wide variety of activities and interests, including this exposition of chaos theory and the Demoscene. And he also has an entry in the Demo for Block Party. Kirk obtained a Bachelor and Master's of Science in Mathematics from the University of Michigan Dearborn. His area of study includes modeling and numeric solutions of dynamic systems. By day, he is a CAD systems administrator in Detroit's automotive supply industry. His advocations of music and applied mathematics are also evident in the chaos theory and the Demoscene talk and demo entry for Block Party. I give you Mark and Kirk Lenigan.
Thank you.
Thank you. This afternoon's talk is related to the uses of disorder, chaos theory as it relates to Demoscene. And here we see a 3D fractal on a black background, such as you often see in demos from earlier this millennium, and even until recently, sometimes those are also used. So next slide, please. And here, as a brief outline, we are going to cover what chaos theory is. We're going to speak about fractals, making use of fractals in your demo, other randomness that you can include in your demo, also a special application called Arnold's cat map, and hasn't been used too much in demos that I've seen, but it's pretty cool, it's worth showing. And finally, we'll have a little question and answer session. Next slide, please. First, we'll start out with what chaos theory is not. Jurassic Park is not an example of chaos theory. The drop of water on the back of your hand is deterministic, and small changes in conditions lead to small changes in which way the drop will roll. If the Range Rover hits a pothole, then you'll probably just jump up or go somewhere else. So this is really not chaos theory, but it kind of got the public interested in chaos theory, so maybe it's worth something. Maybe even $8, I don't know. Next slide, please. Chaos theory also isn't the butterfly effect. That's kind of more time travel.
One moment, just for clarification, we're talking about the movie, the film, The Butterfly Effect, not the mathematical concept.
Yeah, Ashton Kutcher kind of punked you there. You know, it's not really about that. It's more time travel, alternate. What could you go back? What could you change? But then again, it caused people to kind of study the butterfly effect, and again, maybe worth something. I don't really think that was worth $8, but anyway, next slide, please. Chaos theory is the extreme sensitivity in a dynamic system to a small change in initial conditions. A dynamic system is just a system that varies over time, such as the acceleration of a car. You know, over time, you apply more force, and the car will accelerate. And you have variables that you can do, calculus and diffie-q and other great things if you're there in your math career, or if not, you can do algebra on them still probably. When observing the behavior of the systems with different initial conditions, the results can be so different to seem random. Like you'd think that if you stepped on the gas a little more in your car, that the car would accelerate a little bit more. And that's a linear relationship. We're talking about a nonlinear dynamic where in a system such that you made a small change in the constants of the system, and then you got a large change in output, or even an unpredictable change in output, or oscillating between different changes, and you really can't hardly, you're in a realm where you really can't hardly see what the change will be based on your inputs. Next slide, please. Oh, I'm sorry, before we go next slide, I got the butterfly. This effect was first seen by Edward Lorenz in the early 1960s with the basically first solid-state computers, and he was trying to model the weather. He was modeling it out to 6 decimal places, and he got an answer. And then he went out to 3 decimal places, and he got a radically different answer. You'd think that the 10,000th place on out would not matter, but it turns out it did. So he came up with the idea of minor changes causing major changes in the output. So his famous question was, can a butterfly flapping its wings cause a hurricane halfway around the world?
I'd just like to add one more thing about Edward Lorenz and his discovery of the butterfly effect. It actually took place because he was building computer models of global weather systems. And what he would find is that he could compute on the computer that he was using to double precision. So say, for example, 6 places past the decimal or 10 places past the decimal, but the computer could only store single precision numbers in its memory. And since he's modeling global weather systems, these are really long computer runs, hours and days at a time on mainframe computers in the 1960s. So frequently it was the case that his job would be stopped. The memory would be stored to disk or tape or something like that, another storage medium that's more durable. And then later, that simulation would be started up again when there was more computer time available. And what he found was that when the single precision number was fed back in, he would get radically different results, so that if he ran the entire simulation from beginning to end, he would probably get a weather system, a global climate similar to what we are experiencing. But what was most frequent when he put the single precision number back in when the job was stopped was what he termed the white Earth scenario, where the Earth ultimately falls into this solution of the global weather system that it's permanently frozen. Hence, the entire Earth's white. The seas are frozen, snow is all over the land masses. And that's what triggered his interest in these nonlinear systems. And now we'll go to what are fractals, since we're going to be seeing several of them in some of the demos that we'll play later. Fractals are geometrical shapes which exist in fractional dimensions between the 3 dimensions we normally perceive. So, for example, the Mandelbrot set that we see next to it here, the regions that are not black and not blue, between those two darker regions, that's actually an infinitely long graph, thank you. And you can think of it as that line that is infinitely long has a dimension that is somewhere between, it has a dimension somewhere between 2 and 3 dimensions, even though it's a flat graph of a set. So it's existing on a plane, but its actual dimensions are perhaps, say, 2.3 or 2.4, and that's where we get the idea of fractal, is that the term fractal is telling us that you're thinking about dimensions in a way that's different from what we usually do, that we think of integer dimensions. This is more continuous over the 3 dimensions of space. The other thing is that fractals are self-similar at different distance scales. So if we were to zoom in on different regions of the Mandelbrot set, we would find a complete duplicate of it at a smaller distance scale. And you could do it again and again and again as long as you have enough computational resources to keep cranking through the equations that generate the set.
And as Nightshade was saying, they have fractional dimensions. And there's different ways you can construct them just as a static display. Like this one, it's called Cook Snowflake. Why do I say snowflake? You just start with a triangle, and on each center point of the segment on the triangle, you just put another triangle in there, and you keep on adding triangles on the mid part of each triangle, and then it gets more and more complex and rough along the edges, and you get this snowflake kind of design. And it's kind of beyond the scope of this talk, but the actual dimension of the Cook snowflake is 1.26 dimensional. You can see it's kind of rougher than just a straight line, but it's really not a triangle or a square, what you really think of as a 2D object. So this is an example of a fractal, and you can kind of see there, if you zoomed in on one of the parts of the white outline snowflake, you'd get more complete view of the snowflake, and you can keep on zooming in infinitely, so on. And there's other ways you could do that. You start with a square, you get kind of a Greek cross with like plus signs because you add a square in the middle of every square. You let your imagination run wild, like the 3D object where you'd have kind of a germ cell. I mean, basically that you start with a sphere and you had hemispheres on the side of it and so on. You could just go wild with that. That'd be something you could possibly use in a demo if you wanted to. Next slide, please. And the Mandelbrot set itself, complex numbers. Do people know what complex numbers are? If not, I could get into that. The complex number is basically the square root of -1. If you're doing a calculator, mess up, but you can graph a complex number as the real part, the one you're more used to from algebra class or grade school math, and the imaginary part is on the vertical axis. So when a Mandelbrot set is the solution to this equation, z at the next time step equals z at this time step. You square the number, and you add a constant c. C could be any complex number that's solved for. You just try every c. The computer just chew through trying every c. And every c which doesn't make the equation blow up to infinity, like, for example, 1 won't work because you keep on adding 1 to it, the number will get bigger and bigger. It's not bound, it'll go to infinity. But there's other numbers like 0 would work, so 0 is black in the graph here. So you're just plotting as a black point all the actual solutions to the set, and as Nightshade said, the edges are the really fun part, and we'll look at the next slide and see where we're going with that. A Julius set is, we're actually graphing all points that lead to those large changes, the chaotic changes that we saw earlier on. Basically, any place where the graph, like you hypothetically speaking, you move your pen a little bit along the graph, and then the answer at that point was radically different than when you moved, before you moved it. That's a point that will be colorful on this Julius set. And a Julius set is a proper subset of the Mandelbrot set, meaning that Julius set is completely contained within it. And next slide, and we're going back to.
The graphical relations between the Mandelbrot and Julius set. We're going to use fractive a little bit later on, just as we did in our initial talk, to show that basically the Mandelbrot set could be thought of as the master plan of, or perhaps you want to say the one set to rule them all. All Julius sets are subsumed as points in the Mandelbrot set. So, and each individual point in the Mandelbrot set that causes a Julius set to be generated, each of those Julius sets is different. So there's basically infinite variety of the Julius sets. And if you plot a trajectory in 2 dimensions through the Mandelbrot set, you'll basically get a series of Julius sets that seem to animate. And we'll diverge now from the slides and go to fractive? Or? Okay.
See, we were just doing a theoretical background. Now we're actually going to be showing you something graphical you might want to throw in your demo, just Julius sets dancing around the screen.
Well,
there.
I would say what fractive's mainly good for is it's free, first of all. That's always a good thing. And it's good for exploring the mathematical relationship here.
So there's your Mandelbrot set in black. Well, Mark is setting that up. Yeah, now we dealt with the math, and here's some graphics for you to see on the screen. Okay.
Yeah, so wherever the mouse pointer is pointing, it's picking out a single point, and as I get closer to that infinitely long region around the edge of the Mandelbrot set, you start seeing more and more complex shapes, and eventually as you cross the border from the colored to the black part into the Mandelbrot set proper, you start seeing very, very, very complex shapes in the interior of the Julius set, and that's you're basically seeing chaotic relationships between the 2 sets. And we can, it's FAR, or it's FRA, excuse me, QTIVE. So you can download that if you'd like. And now we'll go back to the rest of our presentation.
Yes, that was kind of exploring what you can do with that Mandelbrot set and Julia set. And mainly for demos, you're looking at 2D or 3D pre-pictures. So, you know, you have the math engine behind it, but you're looking at the pictures thus created there. And so, applications of fractals to your demo, like you can pick out a part of the set, zoom in on it, and you see the black color Mandelbrot set in the middle there, and you can pick apart and zoom in on it, and then you get other dancing sets and different colors and shapes around that too. You know, you can change your camera angle, like instead of just simply zooming in on one set where you'll actually kind of be in the black area, you can keep on moving your camera angle and on your demo and stay in the blue, green, dark green, and you know, just get those swirly kind of graphics where colors collapse into each other and such like that, and that's pretty cool in a demo. You've seen that in different demos too. And we can now actually start looking at some demos. Why not? Just turn back over to Mark. And
You want to do that now?
yeah, we can do that.
Okay. Why don't we? Okay. Just a second. This is a demo by Traction called Butterfly Thoughts, and so it's going to reference the butterfly effect and the Lorenz attractor, which are going to fly through as they compute it in 3 dimensions. Okay. Okay, so it's not cooperating. Let's just move on. What's going on here? Where are we going? There we go. So, what happened?
There's I don't know what happened here. Okay. In demos, there's other random, I apologize for the text, I don't know what just happened there, but there's other random effects that aren't chaotic. Basically, you know, you can use random numbers to control, when you have different modules in a demo, you can control which order they appear in or what colors they are. And we were going to show you the demo called Ran by Fusion that shows randomness. It's really not chaos theory, but it's like randomly reordered modules and colors. So let's.
Why don't we go through the rest of the presentation at this point and then do that at the end?
Okay, we can save that for the end then.
Yeah.
Okay, and then okay, and so we'll save that for the end there.
Yeah.
Okay, and there's one other application. I haven't seen this in too many demos, but I could see it being a near future one. It's called Arnold's cat map. Basically, you can take, it's discovered by V.I. Arnold in Russia recently, and basically what you can do is you kind of shear, or you would tilt in the X and Y direction panels of a picture, and then do a modulo division. Basically, you're used to remainder from grade school division, you know, where you 7 divided by 3 is 2, and there's a remainder of 1, so we'd say the modulo 1. And then you use the modulo in the next run-through of the loop. And basically, since that's cyclical, you'll eventually get back to the original image. So you really have this really cool effect of tearing apart the picture, and then after a number of steps, you get the original picture back. So next slide, I'll show the theory on this slide. Okay. And then here,
This one.
it's not working at all.
Hang on. Where did you get it from? I can get it on the web. What do you want to do, Kirk? Okay, skip it. Okay.
Just show the.
You want to go to the demos?
Yeah.
Okay. So this was the random that we had talked about before. No, wait, that's not it. What? Yeah.
Just watch the order and colors of the elements of this demo here.
Wait a minute.
We'll play it through twice so you can see how it's really not the same each time. It's randomizing the colors and randomizing the order of the modules, which geometric shapes you see.
There also should be music here. There we go. There we go.
So you got that, we can show the same one again.
You want to show it
Let's
again
one
so
more
it's
time,
different?
just
Okay.
show it that it's different each time.
Okay. This will be the last time we show this.
So you see some of the effects from the one color are a different color now, and they're ordered differently. It wasn't the kind of blood cells you guys saw the kind of toroid at the beginning there.
Basically what this demo is doing is it's generating random numbers, or actually pseudo-random numbers, and then using those to determine which order it shows the various effects in. And there's it's clocked to the music and the text tags that are popping in every so often. So that's what's giving it some kind of tempo and meter, but the rest of it is just random. You want to?
And there you have it.
There's one more I want to. There we go. Okay. So let's see here. This is Chaos Theory by the demo group Conspiracy, and if I recall correctly, this took second place at, I think it was Breakpoint in 2006. This demo is only 64K in size, so what it's doing right now is using mathematical algorithms to calculate the data that it's going to use later on. Or maybe not.
collapsing kind of effect that we were talking about earlier on about 15 minutes ago. Bit of a Starfield style graphic going by there too. Which itself is based on a chaotic starting point and then going toward the edge of the screen.
Shall we open it up for questions now, or?
Certainly, yes. Any questions?
Yes?
So, unless I missed it, with the various Mandelbrot sets and the Julia sets, how do you determine what colors you're using? Are they just picked at random, or is there something that pops out of the equation that says what color to use when you're plotting this?
I'll take this.
Or like for color determination?
Well, basically, the actual, like in the case of the Mandelbrot set, do I need to put one up there, or have we all seen that enough? In the case of the Mandelbrot set, actually, we'll just go to Fractive here because it's got a good one. Mhm. There's too much. I think I got too much going on this computer. Okay, so here it's only really the black part that is the Mandelbrot set, and then the colors are determined by how quickly the point, any particular point on this in the plane, the complex plane, diverges or converges. Actually, I should say that. Yeah, all points outside the set diverge to infinity. So you don't get, for the recursion relation, it doesn't settle down on a final value, whereas in here, it will settle down. So basically, the closer that color is to black, the darker it is, the slower that particular point diverges to infinity, but it will still ultimately diverge to infinity. And we're only really looking at, like on the complex plane, this region of the set is only about 2 by 2 in terms of units on the Cartesian grid, or whatever you want to call it. So yeah, the colors are how many iterations and how quickly that particular point diverges to infinity if it's outside the set.
Do you remember we had that equation z t plus 1 related to z of t? How many time steps it will take for that to blow up to infinity, really? That's what's controlling. And then you set a spectrum based, any kind of graph you would make, you'd have like if you had a spectrum of temperature, you can make the red over 100 degrees. In this case, the darker color is how fast it will blow up to infinity. Okay?
Okay, yeah, no, that makes sense. Thank you.
Anyone else? Any other questions?
Could you say that to the microphone, please?
Are there any way to do these easily if you suck at math?
Well, the code, particularly for the Mandelbrot set, if you just do a web search for Mandelbrot set and whatever your particular favorite programming language is, although it's easier if it's like C or C++ or Java or Fortran, you really don't want to be doing recursion relations in something like Perl. Because I know you. But basically, yeah, it's the actual recursion relation isn't that hard to program. It's computationally intensive, though, to do the Mandelbrot set. Like earlier, well, I don't know if it was today or yesterday or tonight. It all kind of blends together for me because I spent a lot of time in the block party suite. But I was calculating the Mandelbrot set on my computer, which was an Athlon 64 Opteron 2.2 gigahertz with 2 gigs of RAM. And it was still calculating the Mandelbrot set when I left to come to this talk. So it was only about, it had been going for, I don't know, 2 or 3 hours, and it was only about halfway done with the calculation. So the actual calculations aren't difficult, they're just computationally intensive.
Yeah, it's basically going to be the equation can be expressed in one line of math, and it's complex valued algebra, really, from your basically high school level algebra class, but not just real numbers. You have to have the complex numbers, like where you break that rule where you can't take the square root of -5. It's 5i. It's 2.2 something I, actually. Any other takers? Anybody else have a question for us?
I do have another question. You were talking about with the original Lorentz effect, where he noted that he was saving his data only to X number of decimal places, reading it in and getting far different results than he did when he just ran the whole thing to 5 decimal places, I think you said. I mean, on some of these sets, if I change my precision for Mandelbrot or Julia or any of these sets, what happens to the overall fractal?
Basically, if you change your precision,
Like if I'm doing some of these computations out to 5 decimal places versus if I'm doing them out to 2 or 3, if I'm building these graphically.
if you do them out to 2 or 3, it's going to wind up looking coarser and like essentially kind of like pixelated or lower resolution.
Grainy photo type thing, yeah.
All right, so it does actually create a much finer resolution if you can spare the cycles to go up to a few more decimal places.
Yeah. In fact, this is a Windows-only machine, but there's a program called Chaos XAOS for various of the free operating systems like Linux and BSD and so forth. And that actually allows you you can control how many iterations it will do of the Mandelbrot set based on hitting the arrow keys up or down. And so you can actually see this effect happen, that the set becomes more and more detailed each time you hit the up arrow key. So that, if you wanted to see what effect that precision had, I would just recommend playing with that program.
Okay, thank you.
In the front here?
This is just my favorite model of kind of a discrete chaotic system, which is computer memory.
Okay.
If you have a program running and you tweak a few bits, with alpha particles or heat or something, you get a chaotic effect.
Mm-hmm. Yeah, it's basically, yes, you are introducing something which, at least at this time, with what we know of, it seems like the random rays or quote-unquote bit rot, as they said in the old days, would radically affect this kind of program.
And actually, this brings up something that I'm starting to get interested in, because I haven't really seen much so far of the intersection. Because as the person who introduced us said, I'm a physicist. And it seems that nobody's really playing around with quantum theory and chaos theory, trying to like see how those two fit together. And I think that there might be some fertile theoretical ground there, because that's almost exactly what you're talking about, is an application of quantum theory to everyday life. Because when the alpha particle hits your RAM bank, it's a single quanta in a sense, or at least a bundle of quanta. And so this tiny particle is suddenly causing your computer to become unstable.
Maybe Case can get a grant to study that or something,
Or, Michigan.
Yeah, Michigan's, I wore a blue coat with a maze tie. There's a reason for that, so. Okay. Other questions? Actually, I still want to go after that.
Okay.
I'm not letting this go. We had a little problem there with the presentation to be able to show you the Earth getting torn to bits, like by the Death Star, and then put back together again. But we're going to try and use Google and thieve in somebody else's copyrighted images and be able to show you that.
You want to just close this? It's still acquiring network DAS. There we go. Go for it.
So there's the original cat. Basically they transform in the X direction and the Y direction, kind of tear apart the image, divide, and get the remainder and put it back together. There's your cute kitty getting dismembered. And here's the, this is going to be the Earth at some point. Basically, you look at the picture of the Earth and it's getting rotated and dismembered and putting it back together again. Like I said, modulus division is a cyclic group. Let me put it this way, the integers are a cyclic group under modulo division. And then, so it'll cycle through and come back to where it was. So this would be something that you can have your frame rate set really high if you have it pre-computed. And this would be another nice effect, like a 2D or 3D. You could have a twist in the Z direction for the 3D element. And this might be a nice effect for future demos, if anybody's taking notes or interested in this. I guess I'll open up to questions on the cat map, too, if anybody had a question yet. And well, if not, then thanks for listening, and I hope you enjoy us at NOTACON.